Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC 403. Topic boundary conditions on electric field and electric flux density. Boundary conditions on E and D. So far, we considered the existence of electric field in a medium characterized by epsilon is equal to epsilon naught epsilon r. If the electric field exists in a region consisting of two different media, medium 1 and medium 2, medium 2 characterized by E epsilon 2 is equal to epsilon naught epsilon r2, medium 1 epsilon 1 is equal to epsilon naught epsilon r1. The electric field in medium 1 is E1 and the electric field in medium 2 is E2. If the electric field exists in a region consisting of two different media, then the conditions that the electric field must satisfy at the boundary are called boundary conditions. Before going to discuss about boundary conditions, the electric field in medium 1 E1 can be splitted as its tangential component and normal component ET1 plus EN1, and E2 is equal to ET2 plus EN2. The electric field in its tangential and normal components, the electric flux density in its tangential component and normal component. Now the boundary condition 1 is ET1 is equal to ET2. At any boundary. What it means is the tangential component of electric field in medium 1 is equal to the tangential component of electric field in medium 2 at any boundary, or the tangential component of electric field is continuous across any boundary. Condition 2 is equal to dn1 is equal to dn2, dn1 minus dn2 is equal to rho s. It is except at conductor boundary, and it is at conductor boundary. The physical significance of condition 2 is the normal component of electric flux density in medium 1 is equal to the normal component of electric flux density in medium 2, except at the surface of a perfect conductor. At the conductor boundary, it is dn1 minus dn2 is equal to rho s. Once again, I will read. The normal component of electric field flux density is continuous across any boundary except at the surface of a perfect conductor. Let us continue our discussion with condition 1 in next slide. The boundary condition 1 is ET1 is equal to ET2. We are going to derive this equation based on the closed line integral of E dot dl is equal to 0. Let it be equation number 1. Now, for that, consider a rectangular loop on the boundary of two media. Let us assume z equal to 0 plane is the boundary, z greater than 0 characterized by medium 1, z less than 0 characterized by medium 2. Now consider the rectangular loop on the boundary the length along, let us assume it is x-axis delta x, the length along y-axis, let it be delta y. Now normal to the boundary is z-axis, E1, E2 in medium 2. Now E1 in medium can be splitted as its tangential component and normal component. The angle made by electric field in medium 1 with respect to normal is theta 1, and E2 can be splitted as ET2, EN2, and angle made by electric field with respect to normal in medium 2 is theta 2. Now here it is ET1 tangential component in medium 1, and it is ET2 tangential component in medium 2. Now it is EN1 normal component in medium 1, and it is normal component in medium 2. Now from this equation, the closed line integral of electric field is equal to 0. That is integration from 0 to 1 plus 1 to 2 plus 2 to 3 plus 3 to 4, 4 to 5, 5 to 0. It is equal to 0 based on equation 1. Now let us expand equation 2. Equation 2 from 0 to 1, in this region, this can be split as En1 delta y by 2, 1 to 2 Et1 into delta x, et1 into delta x. From 2 to 3, it is minus en1 into delta y by 2. From 3 to 4, minus en2 delta y by 2. And from 4 to 5, it is minus et2 delta x. 5 to 0, en2 delta y by 2 equal to 0. Equation 3. And as delta y tends to 0, the rectangular loop becomes boundary, and if it is 0, then the terms associated with delta y will be equal to 0, and the remaining terms are et1 delta x minus et2 delta x is equal to 0. Let us continue our discussion in next slide. As delta y tends to 0, et1 into delta x minus et2 into delta x is equal to 0. Equation 4. As delta x cannot be equal to 0, so the term et1 minus et2 must be equal to 0, and it will become et1 is equal to et2. Let it be equation number 5. The first boundary condition is satisfied. The tangential component of electric field is continuous across any boundary. And from the previous figure, you can write the equations sine theta 1 is equal to et1 by e1. It is equivalent to et1 is equal to e1 sine theta 1. Let it be equation 6. And similarly, et2 is equal to e2 sine theta 2. Equation 7. And by applying cos theta 1 is equal to en1 by e1, and en1 is equal to e1 cos theta 1, en2 is equal to e2 cos theta 2. Uh, Remember these equations 6 to 9 to determine the law of refraction of electric field in the upcoming slides. Now here it is boundary condition 1. The tangential component of electric field is continuous across any boundary. Let us move to next slide to derive condition 2. Consider a cylinder on the boundary of two media. Here, the condition 2 can be derived based on Gauss law, that is closed surface integral of d dot ds is equal to q. It is boundary z equal to 0 plane. It is cylinder, and d1 medium 1, d2 medium 2, dt1 dn1. The angle made by d with respect to normal is theta 1 in medium 1, and in medium 2 it is dt2 dn2. The angle made by d2 in medium 2 with respect to normal is theta 2. It is delta s. The height of the cylinder is delta h dn1 in medium 1, dn2 in medium 2. From Gauss law, let us assume it as equation d. In a closed surface, d dot ds is equal to q, as delta h tends to 0. The cylinder becomes boundary. Now, this can be written as dn1 into delta s minus dn2 into delta s is equal to q. That is dn1 minus dn2 is equal to q by delta s. Charge per unit area is surface charge density, and this can be written as dn1 minus dn2 is equal to rho s, where rho s is the free charge density that is placed at the boundary. If there is no free charge, if there is no free charge, uh, the term dn1 minus dn2 is equal to 0, and it is equivalent to dn1 is equal to dn2. Equations 11 and 12 constitutes boundary condition 2. The normal component of electric flux density is continuous across any boundary except at the surface of conductor boundary, and at the conductor boundary it is dn1 minus dn2 is equal to rho s. The two conditions are derived. Uh, the law of refraction of electric field. Uh, in the previous slide, we derived ET1 is equal to ET2, and dn1 is equal to dn2. If the boundary is here, If medium 1 is dielectric and medium 2 is also dielectric, then these two conditions will be satisfied. Uh, they are ET1 is equal to ET2, DN1 is equal to DN2. In the previous slides, we derived equations 6, 7, 8, 9. Once again, I will recall. ET1 is equal to ET2, that is E1 sine theta 1 is equal to E2 sine theta 2. Let it be equation 13. And dn1 is equal to dn2 and d is equal to epsilon e. So this can be written as epsilon 1 e1 cos theta 1 is equal to epsilon 2 e2 cos theta 2, equation 14. And from equations 13 and 14, we get tan theta 1 by tan theta 2 is equal to E1 by E2, where E1 is equal to epsilon naught epsilon R1, E2 is equal to epsilon naught epsilon R2. And after further simplification, equation 15 will become tan theta 1 by tan theta 2 is equal to epsilon R1 by epsilon R2. And this equation is called the law of refraction of electric field at a boundary of free of charge. Once again, I repeat, equation number 16 is the law of refraction of electric field at a boundary of free of charge. Sample problem 1. Here z equal to 0 plane is the boundary. Electric field in medium 1 is given, and medium 1 is characterized by epsilon r1 is equal to 4, and medium 2 is characterized by epsilon r2 is equal to 3. Now we are supposed to divide electric field even in terms of its tangential component and normal component. Now here it is 5ax minus 2ay plus 3az. Uh, z equal to 0 plane is the boundary, means z greater than 0 is medium 1, z less than 0, z less greater than 0 is one medium, z less than 0 is another medium, and normal to the boundary is z axis. So here the normal component is associated with az, and the remaining is tangential component. And based on these two parameters, you can apply ET1 is equal to ET2. Here both the medias are dielectric, so dn1 is equal to dn2. By substituting in relevant parameters, you will get the value of E2, and angle made by the electric fields. The angle made by electric fields, by applying the property of triangles, you will get theta 1. Theta is the angle made by electric field with respect to normal, and the angle made by electric field with respect to tangential component or with respect to boundary, it is alpha with respect to boundary. In such a way that alpha alpha 1 is equal to 90 minus theta 1, alpha 2 is equal to 90 minus theta 2. That is alpha 1 plus theta 1 is equal to 90 degrees. Alpha 2 plus theta 2 is equal to 90 degrees. Based on that, you can determine the angle made by electric field or electric flux density with respect to normal or with respect to boundary. If it is with respect to normal, then it is theta. If it is with respect to boundary, then it is alpha. And the energy densities in both the medias. In the previous lecture, we discussed about energy density small we. It is equal to half into d bar dot e bar, or it is equal to half into d is equal to e epsilon naught e square. And in medium 1, you know the magnitude of electric field. In medium 2, you know the magnitude of electric field. Substitute to determine the energy densities in both the media. The units of energy density are joule per meter cube. And regarding d, at this point, you are supposed to determine the energy density. Here, z equal to 0 plane is the boundary, and above the boundary it is medium 1, below the boundary it is medium 2, and 3 comma 4 comma minus 5. Minus 5 is z-axis component. It will fall in medium 2. So to determine the energy is the volume integral of energy density. The units of energy is joules. Now associated with minus 5, above 1 meter, below 1 meter, this region will fall, and this region belongs to medium 2, means you have to consider energy density in medium 2 to determine the energy at this point, which is covered by the volume given by the specification. The ranges of x, y, and z are given. Energy density in medium 2 along x, along y, and along z, the lengths are given. And based on that, the calculated energy density associated with the area, which is centered at 3 comma 4 comma minus 5. Practice problem. Follow the same procedure and determine the parameters. Thank you. We will meet with the next lecture.